But we know we can, this can be also written as 4 times the mass flow rate divided by the dynamic viscosity, the diameter, in pi. I'll probably put a footnote. I'll do a footnote video with this conversion here and another conversion we're gonna have to do for this question, so that this video doesn't get too long. So if you want to know how this came to be, you can just click on the video. All right, now for this we have information, right? Very important. Which mass flow rate do I put here? Do I put the total mass flow rate or just the mass flow rate per tube? To answer that, we need to think about this guy here, right? This diameter is the diameter of one tube, correct? Note that we have in the heat exchanger, we have, actually not this, we have 2 passes. So something like this. Something like this, and we have 30,000 of these guys, right? My diameter here is in respect to one of these tubes, not for the whole thing. So if I were to put the, what was it, 3, that we just found 3 point something, the 3.42 times 10 to the 4th, I'll be saying that, the mass, I'll be looking for a Reynolds for a very big mass flow rate, assuming the diameter of one single tube. That would make no sense whatsoever, right? So we need to ensure we're using the mass flow rate of a single tube. So that, in that diameter is what gives it away, okay? So that's 4 times 1.14 divided by dynamic viscosity is here, 8.7 times 10 to the minus 4, or 8.6. 8.6 times 10 to the minus 4 pi, and the diameter is 25 mils, so 25 times 10 to the minus 3, which gives me a Reynolds of, where's my Reynolds? 67511. Okay, this guy is greater than 10,000, which is my critical Reynolds for a internal convection situation like such. So therefore, this guy is a turbulent flow. So we have a situation in which we have turbulent flow and we have a fully developed flow. So we go back to our equations here, and we're going to look for the correlation for, where are my correlations? For Nusselt. Here you go. So flat plates, not interested. Pipes, that's what I'm looking for. Undeveloped, not interested. Fully developed, there you go. Laminar, no. Turbulent. This is the one I'm looking for. So I'm going to be looking at this correlation here. Let me write it down so we can take it to the side with us. 23 Reynolds to the 0.8 and Prandtl to the n. N is 0.4 if the fluid is heating, and 0.3 if the fluid is cooling down. In our case, our fluid went from 20 to 34, so it's heating up, so 0.4 is what I'm interested in. So 0.4 it is. So let me grab this, and we can take it with us. Where are we? Here we are. Okay, so I'm going to use Nusselt, correlation for Nusselt. What was it? 67511 times 0.8. Prandtl, 5.85 to the 0.4, which gave me a Nusselt of 340.5, 340.5 approximately. And we happen to know this has to be equal to exactly what I'm looking for, the convective transfer coefficient, the diameter, CL, characteristic length, and the conductivity of water. Right? We can grab conductivity of water off the table. So this is going to be 340.5 times the conductivity of water, which is 0.614 divided by diameter 25 times 10 to the minus 3 meters, which gives me about 8,363. 8,363 watts per meter squared per Kelvin. So multiplying watts per meters per Kelvin, dividing that by meters, so we get meters squared. Cool, that was the second part, right? We found what is the internal heat transfer coefficient. Third part asks us to find out what is the overall convective heat transfer coefficient. To do that, so number, where we want to be here, I guess, number 3, we're going to find what is U. To do that, I know that U, if it's a thin walled situation, I can ignore the conductive resistance. It's going to be 1 over HI plus 1 over H outers to the minus 1, right? Once again, to find this correlation, we talked about this before this was explained. I'll leave a footnote video on the corner here. So if you want to know how this came to be, if you forgot and you want to go back and remind yourself, then you can go there. But here, we're going to go straight into it because this is 1 over 11 internal ones that we just found, 8363 plus 1 over 11,000, 1, 2, 3, to the minus 1, which gives us 4,751 approximately. Okay, same units because we're just summing up things with the same units. And that is the answer, right? So, how good there. Okay, next thing. What is next? So, we can probably put a little footnote here. So, assuming R of conduction way smaller than R of convection. And this comes from the thin-walled statement that we read in our problem statement, right? So pretty much we would have going from the steam water pipe there into the liquid water pipe into the steam, we would have the resistance of the water in the tube, then the tube, and then the steam, right? This one here is a conductive one. This one's way smaller than the other ones. So we need to do some of these two up to figure out what is our convective heat transfer coefficient. And the walls, thin wall means not only that the conduction one can be ignored, but also that the wall is thin enough so that the outer and inner areas are very similar. So the last part of the question is asking us what is the required length. Oh, no, sorry, we still need to do the delta T log mean, right? We didn't do here. So delta T log mean will just be the natural log of the differences, right? So the difference minus over, I can check here. You don't need to memorize these things. So they're going to be here somewhere. This, by the way, is your equation sheet, right? So we're going to have access to all these equations. So delta T log mean temperature difference is just the difference of the differences divided by the natural log of the ratio of the distance of the differences. Okay, so this is just going to be 30 minus 16. So 30 minus 16 divided by the natural log of 30 divided by 16. So this gives me, again, remember that this has to be a number between 30 and 16. It's a mean after all, right? And I got this to be 22.27 Celsius or Kelvin because it's a difference, right? So if we were to do Kelvin, this would have 273 on both ends, so they would cancel each other out, and we would have the 30 Kelvin difference, 16 Kelvin difference there. Okay, so this is part 4, and like I said, we could have done this from the very, very start and just didn't do it so that we can follow the order. And then for part 5, we're asked what is the length of this guy. So the length is, I guess, the trickiest part just because we need to remember that the length needs to take into account the 30,000 tubes we have in tube pass that each tube does, right? So like I said in the very beginning, this is a tube, right? And then it goes twice. That's what 2 pass, 1 pass, 2 passes. And then the L is this L here, right? So that means that the area, in this case here, the area through which heat can be exchanged, the internal area of this pipe here, will be our pi dL, or 2 pi RL, which is the area of a cylinder, right? The side area of the cylinder there, times the 30,000. So the 30,000, let's do 30,000 like so, tubes times 2, right? Times 2, because there's, for every 1 L, there are 2 times that area, right? So it's like we're mirroring this. right? If I just did this first part here, I would have the area of the cylinder here, but since I have two passes, it means I'm doubling the area for each tube that I have, right? Brilliant. And I also know that the amount of heat transferred can be found using the delta T log mean relationship. Okay, so if I want the area, all I need to do is take the Q, which I've known from the start, divided by the overall heat transfer coefficient that we found, and the delta T log mean that we found as well. So this is 2 times 10 to the 9th watts. We're dividing this by 4751 overall heat transfer coefficient and 22.27. Sorry. Okay, let's just check units as we go. This is watts on the top there. And then we have watts per meter squared per Kelvin. And then we have Kelvin or Celsius on the bottom because it's a difference in temperature. So we're left with meter squared, which is great. Unit for area. And this gave me 18,903. 18,903 meters squared. Now, this in turn has to be equal to these guys here, right? Okay, so this means that L will be my 18,903 divided by pi, diameter, which is 25 times 10 to the minus 3, 3 times 10 to the fourth number of tubes, and then 2. And if I put all this together, what I get in terms of units is pretty simple because I have meter squared over here, and then non-dimensional, and this is meters, so it's going to be meters. That's my answer, right? And then what I get here is 4.01 meters, approximately. Okay, and that will be the answer for my part 5. All right, with that, we finish the 2020 final exam. I hope this helped you out. Try to go faster on this problem because, as you see, it's a big problem. It's a long one. It involves a lot of the things we've talked about during the heat and mass transfer course. And I strongly encourage you to try to solve it on your own and just use a video as a help when you need help instead of watching how to do it from start to finish. Okay, like I said, I'll record a video showing the theory behind the two things that I've mentioned before. If this helped you out, consider liking the video. If you have any questions, just leave them down below on the comment section. And if not, we'll talk soon.